Okay, we are beginning our unit in magnetic fields and forces, and we're going to start with a bar magnet. Okay, and here's the north pole of a bar magnet. I am assuming that sometime during your interest in science that you have had the opportunity to play with a couple magnets and see what they do, okay? And that, you know, they stick, okay, and they push, right? And that you find out that if you actually have them labeled as a north and a south pole, that the same idea, that follows some of the similar ideas as electricity, where like things repel and opposites attract and that sort of thing. We are getting into an area of the school year, getting into a time of the school year where I slowly watch you guys descend into patheticy, okay, where you become pathetic, okay, and you seniors, primarily seniors, you juniors don't get dragged down with them, but you guys just start becoming blithering, babbling idiots because of all the other stuff that's going on. Oh yeah, and you're about to graduate from high school, and you get into the and you're getting into the IDGAF mentality. Okay. Okay. Right. And so here's the thing. This unit comes at a really poor time because some of these things. This is a very weird unit. Magnetism is spooky. And there are certain things that I'm just going to have to ask you to accept on faith. That this is how it is. It's been empirically determined. This is how things behave. Don't ask me why. It just does. Okay?
Does textbook try to tell us why?
Now, the textbook. The textbook will try to explain you why and get down to the molecular level and, on magnetic dipoles at the molecular level and that sort of thing. And I don't want to bother with that because it's not important for what you guys need to know. And frankly, we don't have time. So, that being said, this is actually really cool too. There's some really fascinating stuff that goes on here. And the whole idea of magnetic fields and forces is the origin of almost all of our electricity. All the electricity that we get comes from these phenomenon in one way or another. In fact, the only one that doesn't is solar. And solar is according to Einstein's photoelectric effect. That sort of an aside that Albert Einstein won his Nobel Prize in physics, not for relativity.
Oh, really?
It was for the photoelectric effect. Yeah.
But did it influence relativity?
Well, the photoelectric effect had more influence on quantum mechanics than it did relativity. Okay, so here we have a bar magnet with a north pole, and we have some distance of separation with a south pole, and in between, okay, we have. Okay, in between we have our magnetic field. It is another kind of field. Now, magnetic fields follow a lot of the same principles as electric fields. Okay, there are arrows to them. They have vectors. They point from a north pole to a south pole direction. Okay, and then as you get these boundary effects as they go out. All right, and then if you just take a single bar magnet, you also have this sort of thing expands. So we have, if here's a north and south, then it's not just looping like this. These lines will go out and it'll curl back on itself. Like so. Okay. Now here's the interesting thing though. Where magnetic fields go from a positive to negative, Okay, is the direction of the field. Bar magnets or magnets, they don't have, you can't have an isolated north or an isolated south. They do not have what is called a magnetic monopole. Okay, every magnet must have a dipole. Okay, and because every magnet is a dipole, okay, these magnetic field lines don't stop here. They actually travel through the magnetic material. And so each one of these completes a loop. Okay, now these lines do not actually cross each other. Okay, those rules still apply. Okay, that the lines don't cross, but they can get really, really, really close. And so within the magnet itself, the field lines are looping within themselves. So logically it also doesn't work either. So if we were to take, imagine we were to take our bar magnet and cleave it in two, okay, which is, fancy speak for cut it in half. We'd start with the north over here, and we'd finish with the south, but because these magnetic fields travel in loops, if we cut them in half, then what would we have on this side?
North.
Well, we'd have a new north, and we'd have a new south, and we'd have loops going this way, okay, and loops coming around.
So weird.
Like so. All right, so so if you take this, reductio ad absurdum, okay, and you reduce it to its, the smallest portion. You take this material and you reduce it to its smallest particle that still has its ferromagnetic, magnetic properties. You will still have a north and a south pole to it. And the way we tell, by the way, whether or not we have or the direction of our field is we use a compass. Okay, so you put this compass needle in here. Okay, and the compass will point south. It will always point along the lines, and your compass will always point south. So when you take your compass and you're out mountaineering or whatever, you're hiking, and you notice, oh look, the needle is pointing north, right? Well, because all of our mountaineering and all of our maps is very Eurocentric, okay, we've established that the North Pole is, the European, Russian, even the Chinese hemisphere, okay, and that's north, even though, China's in the northern hemisphere, okay, even though they totally act like a southern hemisphere country. No. Okay. No, the point is that the Earth's magnetic field. Okay, so here's the Earth, and we've got
Can see half of it, like the northern hemisphere. It looks like watermelon.
Yeah. Oh, you guys can see it. Yeah, not bad. See?
Whoa.
Okay. That's what I was doing. Yeah.
Where's Cuba?
Seriously, you guys. Madagascar, Cuba. All right. All right. That the magnetic fields that the Earth has.
That was quick.
Goes like that. Which means that what we actually call the North Pole is actually magnetic South Pole.
Oh my gosh.
I know.
Are you cool?
I know. So
we're upside down.
now, yes, we're upside down. Now, before this changes with a relatively regular pattern that the Earth's magnetic field will flip. every 20 to 50,000 years or so. Okay, and guess what? We are overdue. There is evidence that we are in the midst of one of the flips coming very soon, and it happens like almost instantaneously. Yeah, well, on a geological timescale, it happens. Well, it'll happen over the course of about, say, 5 to 10 years, and we'll just go.
What happens?
Does it churn?
The magnetic.
Wait, so it churns like that, or does it actually like go through?
I'm not sure exactly what happens, but our magnetic field is the evidence of a rotating iron nickel, a hardened iron nickel core at the center of the planet, and as it precesses, it spins, and it kind of does like if you spin a football and how you get it to spin on the end, it kind of does that, and that's what causes the. So it kind of rotates funny, and then it kind of like wobbles off, and then it corrects itself and starts spinning the other direction.
To our daily life? When the
Oh, we need to pause this discussion for a minute because we have a lot we have to cover.
Okay.
But if we can get through this lecture in time, we'll talk about what the effects of an alternating magnetic field would be. Okay. So. All right, we have a variable for this. Okay, this magnetic field. Okay, the variable for it is B.
Can't see.
Okay, it is B. It is a vector, and it is a measure. Okay, it's a measure of the strength of the magnetic field. That is B. Now, here's an interesting thing. We're going to take a charged particle, and we're going to put our test charge into our magnetic field. Okay, there it is. If it is, it's a test charge, so it would be positive. Okay. And if we just put it there and just set it there, nothing happens. But if it moves, then interesting things happen. Okay, and it experiences a force. So we're going to move our particle in that direction. The force that will act on this particle, will point into the page. Huh? That's right. And this is where things start getting difficult for you seniors, because you actually have to start thinking in ways that we're generally not trained to think here in America. Okay?
Common core.
We need to start thinking in all three of our dimensions. What this is, the force is the product of, or is the result of a cross product. And so we're going to need our right-hand rule. And here's how we determine the direction of our force. You take your fingers and you point your fingers in the direction of motion. Okay, so our charge is going to move in that direction. Okay, or actually we're going to need to go this direction, because the field is where we're going to curl our fingers. Okay, our thumb, which is, here's my thumb, right? Okay, it's down and into the page, which means this vector here. And I know I've introduced these vectors to you.
I, J, and K.
Yeah, it's the arrow, right? And so if you're shooting an arrow away from you, okay, then you get to see the tail feathers. If you are the lucky recipient of an arrow shot at you,
It's a dot.
okay, it is a dot, because that's the last thing you see before it hits you is the tip of the arrow.
And die.
All right? Or at least you poke an eye out. Okay, or you're the zombie that just got, taken out. So, if Daryl shoots his crossbow at you and hits you.
Yes.
Okay. So, Okay, so we now have 6 directions for arrows. We have left, right, up, down, and into the page, out of the page are our 6 directions for arrows. Yeah? Okay. So, we have a formula for this. That the force due to the magnetic field, okay, is proportional to 3 things. It's proportional to the charge on the test particle, which should make sense, that the greater the charge, the more force it's going to experience.
Yes.
Okay? It is proportional to how fast it's traveling. The faster it moves, the more force it's going to experience. And then finally, that vector is crossed with the magnetic field. And this is an important equation.
So is that why you like electromagnets work?
We're getting there. But yes. Okay.
So if it's the same direction, they become 0? V and B?
Well, if we're to do the magnitude of this vector, it's Q, V, B, sine theta, right? Okay, or sine of the angle between V and B, right? That's what a cross product is. This is the magnitude of the vector. The direction of the vector is determined by RHR, which is right-hand rule. Yeah? Now, make sure that you write it as V cross B, not B cross V, because that will change the direction of your vector. Okay? It is a order dependent product is cross product here. Okay. So what are the units for this? Okay. The unit for B is a Tesla, named after Nikolai Tesla, who like Faraday, is one of the unsung geniuses of electromagnetism. Okay, they didn't have a whole lot of formal training. They figured out a lot of this stuff on their own, and were still pioneers and inventors and thinkers on the forefront of electricity and magnetism for their time. A Tesla, given by the letter T, and it equals, okay, so if this is B, so we're going to divide this by Q and V. This is going to be a Newton. Here's how I'm going to recommend how you think about it. It's a Newton per coulomb per meter per second. Okay, so what's that? So for the same amount of force, for an equal amount of force, your Tesla is going to have to be bigger for. I'm sorry, your Tesla will. They're proportional. Okay, that your Newton, your force and your velocity are proportional. Your force and your charge are going to be proportional.
Newton over Coulomb, isn't that something that's E, right?
Newton per coulomb?
That's E.
Is that what?
Electric field.
Uh-huh.
Electric field over...
Okay. Now, okay, I'm glad that you guys are thinking like that. Stop for a little bit. I don't want you to get too much into this yet. Okay. This actually, or another way of writing this in newtons seconds per coulomb meter. But that's just if you flip it around. But I want you guys thinking about it like this: newtons per coulomb meter per second. Okay. So what we're gonna do, I'm gonna give you guys some examples, and we're gonna stop the clock here. And so if you want to watch this again. We're going to create the examples on another video. So, example 1. In fact, I want to keep them color coded. All right, and the charge is positive test charge is traveling that direction. Okay, example 2.
Is that x direction?
That's a vector. That's the vector. Okay, that's example 2. Example 3, and then example 4. Okay, so those are your examples. You guys draw them in your notes, and I'm going to give you guys a little bit of time to, what I want you guys to do is draw the force vector that is experienced by the test charge moving in the direction shown.